Okay, welcome. So what we're going to be working on today is going to be just a continuation of the some of the topics in fluids. Now these are going to come fast, so I'll try to essentialize it as much as I can. But like I say, they will be starting to come a little bit faster, and hopefully we'll get just the essentials of what we need to know. So I'm going to go ahead and share the screen with you. No, whoops, I don't want to share it here. I want to share it on here. My bad. Whoop, okay. I see. There we go. Okay, so I wanted to really quickly do a an example problem here. This one says a reservoir has a surface area of 50 kilometers squared and an average depth of 40 meters. What is the mass of the water held behind the dam? Now, in these ones, if you're not told what the density of the water is, you can assume it's just 1 gram per centimeter cubed. Now, as a reminder, this converts to 1,000 kilograms per meter cubed. Okay. So now what we need to do is we need to find the volume of this water. So the volume, basically it's going to be the area times the height. We don't know the shape of the lake, but we do know its surface area and then its average depth. So basically what we're going to just treat this thing as if it's got a constant depth of 40 meters and it's got this area on the top and the bottom is basically, that's an approximation, but that's basically what we're going to do. Now, unfortunately, these units don't quite work out. You can't just multiply 50 kilometers squared and 40 meters squared. So 50 kilometers squared, well, we need to convert this to meters squared. So the best way to do this is going to be to have 1,000 meters per kilometer. Not five, but per 1 kilometer. And then we got to square both of those. So it's really 1 million square meters per kilometer squared. And this is going to give us 50 million square meters. Okay. So there's 50,000, 50 million square meters. All right. So that's just something to keep in mind. Okay. That when you do that conversion, you do need to be careful with it. You can't just do a straight kilometers to meters because you're dealing with square units, not just with the linear units. All right. Now, if we want to do the mass, what we're going to do, the mass of the water, as a reminder, density is the mass divided by the volume. So the mass is going to be the density of the water times the volume of the water, which will be 1,000. That's the density times 50 million. That's the volume. And when you do this, this will give you 50 billion. So that would be 5.0. Just do 3 sig figs times 10 to the 10th. So yeah, it's 7 and then 3, the 50 million is 10 to the 7th. 3 more would be 10 to the 10th. So 50 million kilograms. Okay. Oh, I just multiplied by the area. I never found the area. I found this was the area. This was not the volume. Okay, so we gotta go back and we gotta find the volume. I was thinking it doesn't seem quite right to me somehow. But in any event, I found the area. So this was the area. Now I need to multiply by the volume. So this will be 50 million times 40 meters of depth, which will give you, that would give you, so times 4 would give you 200 million, times 40 would give you 2 billion meters cubed. Okay. And then you would multiply that, the volume, the density, the mass of the water would be the density of the water times the volume, which would be 1,000 times 2 billion. And I'm actually just going to replace this and we're going to do 3 sig figs. 2 times 10 to the 9th. So 2.00 times 10 to the 9th. And then this will just end up with us 2.00 times 10 to the 12th kilograms squared. That's 2 trillion kilograms, by the way. Okay. So that is what we're dealing with right there. All right, so that is one of the ways you would do this. Now, an alternative question that could be asked, something that might be asked, question, what is the pressure? So this is the mass of water that the dam holds back. What is the pressure at the base of the dam? And this is where the base of the dam. This is where it turns out that you might think you need this mass. You don't, okay? Because the pressure, the fluid pressure of the water, is just equal to the density of the fluid, gravity times height. Okay, so this would just be 1,000 kilogram per meter cube. Got to make sure you're in that SI unit times 10 meters per second squared times 40 meters. And you can see that it's just 400 times 1,000, so it would be 400,000. And then the units are pascals. Or we could also say it would be 400 kilopascals. That's another way of doing it. 400,000 pascals would be the SI though. Okay, so that is how we would do that. That's just a quick review. All right, so from there we will go on to discuss. Just going to call this Pascal's principle and fluid equilibrium. Okay, to start off with that, what I'm going to do is I'm going to just give the statement of equilibrium. Okay. So statement of equilibrium. And I'm going to try, this might seem obvious, but I'm going to try and give a sense of I'm trying to also give a couple of examples about why this is a relevant discussion of equilibrium. Okay, so the statement of equilibrium is a fluid system is in static equilibrium when the pressure at a given height is equal. All right. And that kind of makes sense because pressure was height dependent, which means that if you, for whatever reason, have different pressures at different heights, then you're going to be not in equilibrium. Okay. That means things are going to have to move around until your pressures do in fact get equalized. All right. So this the basically the basic idea is just that this is that pressure, P at some height is a constant, okay, at a given height. So you should be able to draw a horizontal line through your system and be able to say, okay, the pressures are equal at this point. All right. So I'm going to give you just a couple of examples of how this works out. First example I like is Pascal's vases, and I'll just give a real quick, simple diagram of it. Basically what you have when you have Pascal's vases is you would have something that looks, actually, we'll do it a little bit different. So we'll have one that's just, just a tall horizontal, no, a tall, parallel side. So this could be like a cylinder on one side. On the other side, what we'll have here is we'll have like a funnel shape. And the idea here is that when these things are in equilibrium, basically, what you will have is you will have water at the same height, okay? And it could be any fluid, but basically what's going on is that these two things have the same height of water. And you might think, okay, well, that's obvious. Well, the thing is it's not so obvious. And the reason maybe it does seem perceptually obvious, but it's not immediately clear why that's the case. Because this side is heavier. Okay, there's more water over on this side than there is on the other side, particularly if you can imagine this in 3 dimensions, and this funnel was quite wide. Um, the idea would be that this side was heavier. So how is this lighter mass of water holding up this heavier mass of water? And there's the basic idea is basically what's happening to just give you a quick answer. The wall of the system is actually helping to hold it up. That's kind of what's going on. But the idea is that we can say that this is true based on the fact that pressures are equalized. So basically, what we have right here is we'd have H and we'd have H, and the idea is that pressure on the left equals pressure on the right because it's the same fluid. Density is the same. G is the same. It's the same planet. Acceleration is the same, and your height is the same. Okay. So as long as you're dealing with the same fluid, then you're going to be dealing. Then you'll have equal heights. Now, something kind of interesting can happen if you start mixing fluids. If you mix fluids, like if you put oil on one side, you can actually get it to be higher on one side than the other. This is something that's kind of interesting, worth observing. If you ever get the chance. So the idea behind this is that the pressure is the same on each side. Now, if I try and draw the system again, just try to do it real quick. And the idea here is, well, what if we have, what if we have water only up to there on the right, and then we pour some water, sorry, on the left, and we pour some water in on the right. So basically, we pour water in. Well, now what happens is that this height, the right height, H sub R, is greater than the height on H sub L. Okay, so what this means is it means that the pressure on the left is less than the pressure on the right. And basically, it's just because HR is greater than HL. The densities are the same, the gravity is the same, but the pressure will be greater if the height is the same. Just because, reminder, your pressure is equal to rho of your fluid G H. Okay, so your pressure on the right is greater than the pressure on the left. Now, what this implies is it means fluid will move in this direction. Fluid will move to equalize the pressure. It will move from higher pressure to lower pressure. Okay, so that's the point, is that fluid moves to equalize the pressure. All right. Now, the idea here, I want to talk about some of the things we talked about last time just to kind of demonstrate this point. So the first thing I want to talk about, those are Pascal's vases. The first thing I want to talk about is a barometer. And we can even talk about a manometer. Manometer is a little bit different in that it is a similar to a barometer, but it's for measuring pressure. I'll probably just, well, I guess I could go over both. So if we have a barometer, the idea here, barometer, why I can't spell, but it's barometer. The idea here, as a reminder, what we had is we had I don't need that to be quite that big. We had a pool of mercury down here, and we had a tube that was stuck into the mercury. So mercury is silver. I'll just draw it in purple. Okay. And the idea was that this mercury would fill up like so. Okay. And the idea here is, well, why was this happening? Well, the point was in here was vacuum. So in vacuum, pressure is equal to 0. But out here, we had pressure equals P atmospheric. Okay. Well, the idea is that if we set, I'll do a big bold line here. If we do a big bold line right there on top of the fluid, basically the idea is that we want to have equalization of pressures. So P outside is just equal to the P atmospheric. Okay. But P inside, so if we look at the inside of this column, basically what it has is it has a height of H. Well, that's just equal to the density of mercury, density of, and Hg is the symbol for mercury. So rho times G times the height of the column. And this is the idea, is that you can then say, okay, the atmospheric the P out should be equal to the P in. Otherwise, the mercury would move because it's a fluid, it's free to move. So P out should be equal to P in because that horizontal line gives the condition of static equilibrium. So P out was just the atmospheric pressure, whatever that happens to be. And then you get rho of mercury G, and those two are fundamental constants. You really can't change the density of mercury or the acceleration of gravity. I mean, a little bit, but not appreciably significant. And then you have the H. So the idea here again is that H is, if you watch H change, given that the density of mercury and gravity are constants, the only reasonable thing that could have changed is the atmospheric pressure. Okay, so that's why this thing measures a that's why this thing measures it measures atmospheric pressure. Okay, so that's what's going on here. Now, a manometer is kind of similar. You can have different designs of manometers. I think a lot of them are actually open to atmosphere. I'm gonna draw one that's not open to atmosphere. Just to kind of give you actually, I'll draw one that is open to atmosphere. So basically it looks like this. And what you have in here is you have some unknown pressure. I'll change this just a little bit so it goes up. Like so. Okay, so what you have here is you have some P unknown. Just call it PU. Let's call it P1. Okay, so P1. So P1 equals whatever. And then what you have is you have some mercury in here. Okay. And a lot of times what you will have happen is you will have a difference in height between these 2 points. Okay. Now the point is out here, you have P atmospheric. Okay. Now, what you want to do if you want to find P unknown. So we want to know what is our unknown P. What I'm going to do is I'm going to draw a line, a dotted line right there. Okay. It's a horizontal line. And the idea here is that P on the left should be equal to P on the right. Okay. Now, P on the left, we have the pressure of the left. We have a couple of things here. Okay. So we have one, the P atmospheric. That's what's pushing down on the mercury. But then we also have this, I drew this height here. We also have this density of the mercury. Density of mercury times G times that height. Okay. It should be PR. And then that is equal to the pressure on the right, which the only thing pushing down there is just the pressure from inside this chamber. So this is this unknown pressure that we're looking for, okay? So if we know atmospheric pressure and we can measure this height, then we can determine this pressure inside, okay? Now, you can have these things go, you can have them be at different heights. You can look at the book for this example, but you could have the height be higher on the right than it is on the left. And in that case, that would mean that that the pressure inside was lower than the atmospheric pressure, okay? Because it required this extra mercury to balance it out with atmospheric pressure. So this is a way you can measure unknown pressures, okay? It's kind of a simple setup, just using a couple of tubes and some mercury. Okay, we tend to use pressure sensors, but this is a measurement device. So both the barometer and the manometer are measurement devices. Now, one other thing I want to show you that has implications here is a hydraulic press. All right, and this is actually really cool because of of basically of the implications this has for lifting things. So basically a setup of a hydraulic press looks something like this. Right, so kind of looks like Pascal's vases, but what you have on one side is you have a much smaller. They're both vertical, and on one side you have a much smaller. Then instead, what you do is you cap them both. And like I said, this one on the left, this we'll call this area 1. This would be area 2. And area 1 is greater than area 2. All right, that's basically what we're saying here. Now, the idea here is what you end up doing is you end up filling this with oil. Usually it's oil. You can use any fluid. Oil is typically used because it doesn't corrode anything. So that's why, hydraulic presses typically use oil, but you could use water. Like water would work just as well. All right. Now the idea here is as this is just Pascal's vases, if they're just left to sit there, then this is fine. But what's interesting about what's going on is if we apply some force here, F1, then what you probably know kind of what will happen is basically then this thing, if these things are just like cylinders, if they're free to move, basically you'll get an upward motion. However, the question is what counterbalancing force F2 would balance that out. And the idea here is that fundamentally what's going to happen is that the pressure change due to F1 has to equal the pressure change due to F2. Now, this is interesting. All right. So, and the way we can think about this is we can think about, okay, these are at equal heights. So, I could just draw a line there. And we think about the pressure on the left has to equal the pressure on the right. Now, the thing here is that H1 and H2 are equal. So H1 equals H2. Okay, great. But the other thing we have here, the pressure on the left, remember, we have that force, that F2 creates a pressure. So it'll be F2 divided by A2, and then plus, and we'll just call that H2 equal H1 plus rho GH. And then the pressure on the right is F1 over A1 plus rho GH. Okay, well, we set these equal to one another. What we end up with is the rho GH's cancel, and we just end up with F2 over A2 equals F1 over A1. Well, check this out. This like I say, this does have some pretty significant implications. It means, among other things, that you can support a very large force with a very small force based on their differences in areas. So let's take a look at this. Let's say if F2 equals 10,000 newtons. Okay. And then A2, this is a circle 1 meter in radius. Okay. And then A1 will say this is a circle 10 centimeters in radius. All right, we'll just use that. Okay. So the question then, what we'd be asking for is okay, what does F1 have to be? Now, 10,000 newtons is about 1,000 kilograms. Okay, that's not, that's about a ton. All right, that is about a ton. The question is, how much force do we need to hold that ton up? If we just put a ton on the left portion of this, then it will basically move the right side up. But the point is we don't actually need that much force to balance it out. I hate it when this stupid thing happens. Okay, so the area 2 is just going to be pi r squared, which 1 squared is just 1, so that is just going to be pi. And then area 1 is going to be pi times 0.1 squared, so that will be area 1 will be equal to 0.01 pi. Okay. Now, the question is, okay, let's set this equation up. So we have F2 was 10,000 newtons, so F2 over A2 equals F1 over A1. And we could write this out, but it turns out the pi's will cancel, so that's why I didn't bother. So 10,000 newtons over pi should equal F1 over 0.01 pi. Well, we can solve for F1, and when we do that, we get 10,000 times 0.01 pi over pi. Well, notice the pi's cancel, and then you just get 10,000 times 0.01. That is just 100 newtons, okay? 100 newtons is a very easy force to exert, okay? So this is how hydraulic presses work. If you've ever, it works a little bit differently. In general, the thing is, one of the main problems is you can't push this down very far. The lift doesn't lift much. So what they actually do is they'll pump fluid in to the lift to make that work. But it turns out as long as you pump it in over here, you don't actually need that much force to pump it in and be able to lift up the left side. So this is like how hydraulic lifts in like auto shops work. Okay. So that's one example of that. So that is basically what I wanted to talk about when it comes to equilibrium. Like I say, we would spend, in the course of a full, if we had a full year or whatever, we'd spend a lot more time on this, but we just don't. So I'm going to have to leave it at that and just say, okay, the main thing to remember is that pressure needs to be equal at a constant depth. All right. Okay, so moving on to the buoyant force. Buoyancy or the buoyant force. Now, this is the how this works. The idea behind what buoyant force means is that basically is that submerging an object in a fluid generates an upward force from the fluid. Okay. Now, the reason why this is basically in order to submerge an object, you have to push fluid out of the way. Okay. And a lot of times that means you have to raise the fluid up. If the fluid could go sideways, it would do that just of its own accord. So the fact that it is that, you have some depth of fluid means that the only way for you to push the fluid out of the way is to force the fluid upward. So basically what this means is that the object has to be able to force the fluid upwards, okay? And the fluid wants to go down just like the object wants to go down. So basically you can think about it, the fluid and the object are both fighting to go down. And sometimes the fluid wins, in that case the object floats, sometimes the object wins, in that case the object sinks, sometimes they're about equal, in which case the object hovers, okay? And so we'll talk about each one of those. So I'll just get to that. First of all, types of buoyancy. You have positive buoyancy. And this is what we mean if we have the object is either floating, so like a ship on the surface, you would say that object has positive buoyancy, or it rises through the fluid if underwater. Or if under the fluid, if submerged. Now, an example of this would be if you've ever tried to, you've been at the pool or at the beach, you try and force the beach ball under the water and you let it go, it shoots right up. Okay. So that's what we mean by positive buoyancy. All right. Negative buoyancy. This is basically a sinking object. Um, if you wanted to make a positively or a negatively buoyant object float, you need to attach it to something that was positively buoyant, okay, or insignificantly more positively buoyant. Now, it is worth noting with negative buoyancy, it still experiences a buoyant force. The idea here, though, is that the force of buoyancy is less or is less than the force of gravity in terms of magnitudes. Force of gravity is opposite the force of buoyancy in direction, but the force of buoyancy is going to be smaller than the force of gravity, which means that gravity is still going to win. However, one of the things that happens is the buoyant force does in fact sort of decrease the weight of an object. And you may have if you've ever been playing at the pool, you may have noticed that, you can it's not that hard to just kind of hold up a person with one hand when you're at the pool. And even though you couldn't do that if they were in air, basically their buoyant force, even if they're a sinking object, their buoyant force makes them significantly lighter. So that is what buoyant force does. And we'll get to that in a minute. I didn't include that in positive buoyancy, but in this case, the force of buoyancy is generally greater than the force of gravity. Now, it's worth noting that the force of buoyancy equals the force of gravity if floating. Okay. Now, the whole point is that if the object is floating, then buoyancy can't shoot the object up into the air. I mean, it kind of sometimes it can, but if it's just floating on the surface of the fluid, then at that point the buoyant forces and the gravitational forces are equal because they're canceling out. The object is not accelerating. All right. So that's something to keep in mind for that. And then we have neutral buoyancy. If you've ever gone scuba diving and you underline all of these and you adjust your it's called your BCD, your buoyancy control device, you adjust how much air is in that. Basically what you want to do is you want to make yourself neutrally buoyant. And what a neutrally buoyant object does is it just sort of hovers in the water. Okay. So fish, almost all marine animals have some method of controlling their buoyancy that allows them to hover at whatever depth they want to. Okay. So a lot of times it's the inflating of an organ or something like that. And a lot of times their bodies are very close to the density of water anyway. So it makes it easy to attain that. But when you're scuba diving, you basically you take air from your tank and you manually add it to your vest to inflate it or deflate it. You can remove air, and that will adjust your buoyancy. Okay, so that's what's going on. And in this case, the force of buoyancy is always equal to the force of gravity. It's worth noting that the way this is different is the object is submerged. Okay, it's completely submerged, unlike a floating object. Um, where the force of buoyancy is only equal to the force of gravity if the object is floating on the surface. Okay, so that's the main difference between that. All right, so those are the types of buoyancy. Now I do want to just relate something to density. Density is not always as clear because a lot of times with objects, particularly like ships, yeah, they're kind of composite objects where you can have a metal ship that floats, and basically it's because the ship is like a composite of metal and a bunch of air, and that's why that's one of the main reasons it can float. Whereas, if you just had a solid piece of metal like a nail, you drop that into the water, it sinks, no problem. But in general, the density of the object with positive buoyancy is less than the density of water. So water is a heavier material than the object on average. For negative buoyancy, the density of the object is greater than the density of water. And for neutral buoyancy, the density of the object is equal to the density of water. Okay, so those are the density considerations of the objects experiencing different types of buoyancy. Now, what I want to do is I want to do a quick derivation of the buoyant force. And the idea actually is that there is a differential amount of pressure on the top and the bottom of an object, and that's what actually creates the buoyant force. So what I'm going to do here is we'll do this thing submerged in water. And I'm just going to do let's say it's a box and you have area of the top, area of the bottom, area of the top equals area of the bottom. Now, it's worth noting that, again, like I say, pressure exerts forces on all sides. So what you end up having here is you have a pressure force from the top. So force due to pressure from the top up there. You also have it on the sides. Force due to pressure on the right side, force due to pressure on the left side. But these two are equal. So force due to pressure on the right, I'm just going to call this force of the top, force on the left, force on the right. Force on the right equals force on the left because they're functionally at the same depth. Okay, so they don't really matter. But the interesting thing is that you also have a force on the bottom. And the force on the top does not equal the force on the bottom. And the reason is that the depth or the height is different. Okay, so the idea here is that what we have here is we have the height of the top right there. And what we have there, this is the height of the bottom right here. Okay, so the pressure on the top is equal to or it's equal to rho of water, or any, doesn't matter, it could be any fluid. Rho of the fluid times G times H of the top. And then the pressure on the bottom is equal to rho times fluid times G times H of the bottom. Now, the force on the top, we're going to have to take that pressure and multiply it by the area. So it's equal to pressure of the top times area, which is just going to be pressure, density of the fluid, G, the height of the top times the area. And then the force on the bottom going to be the pressure on the bottom times the area, which is going to be the density of the fluid, G, times the H of the bottom times the area. Now, the net force is going to be the force on the bottom. And I'm going to say the net force is going to be up. So the force on the bottom, because that's the upward force, minus the force on the top, because that's a downward force, okay? So pressure is pushing the box downward from the top, but it's also pushing the box upward from the bottom. All right, so what we get there is we end up with the force from the bottom was rho F G, height of the bottom, A, minus rho F G, height of the top, A. Now notice you can factor some things out here. You get rho F G A, and then you have height of the bottom minus height of the top. Okay, so what you actually get when we look at these two things, what you actually get, and I'm just going to call this purple side, that is H of the box. And I'll do capital H so we don't confuse it, but that's just H of the box. So the whole point here is that this thing is the height of the box. Well, what's cool about this is now we have density of the fluid times G times A times the height of the box. Well, if you're paying attention, what you might realize is that this thing is equal to the volume of the box. Okay, so it's density of the fluid times G times the volume of the box. All right. So that is how we found the buoyant force, and this is the force buoyant. It's the density of the fluid times gravity times the volume of the box. Now, this is if it is completely submerged. Okay. Now, if it's not completely submerged, I'm not gonna go doing I'm not gonna do another derivation. You can, if you want to see that, come to me during one of the lab days when I offer help on this. But in general, the general form of the buoyant force, it is the F buoyant equals the density of the fluid times G times the volume submerged. Okay. So this works for floating objects. It works for sinking objects as well. So it works for any object that has that has that has um that is submerged in the water. Okay. So that is something worth keeping in mind. All right. Now the um there's another thing that comes so I guess I'll go ahead and do this. So we'll just talk about for positively buoyant objects. So for positive buoyancy, buoyancy. And the idea is if the object rises, then F sub, I'll just start calling that F sub B for buoyant force, is greater than the force of gravity, which basically means that rho F G, and then in this case, it's the entire volume of the object, if the object is rising, is greater than mg. So the idea here, and this is how we can ultimately derive that the density of the fluid, G, times the volume of the object, is greater than the density of the object times the volume of the object times G. And notice that the G and the volume of the object will cancel out. So this is just going to leave you with the density of the fluid is greater than the density of the object. Now, if object is floating, so if your object is actually just floating, then F sub B is equal to F sub G. So what this is going to say then is that the density of the fluid times G times the volume submerged is equal to mg. All right. Now, in that case, the what you one of the things that comes up here is that the percentage submerged is percent submerged. And this is I'm going to do this as a decimal. We could actually talk about the fraction submerged. And what that is, this comes up in some of these questions. That's just equal to the V submerged. V sub is just V submerged divided by the volume of the object. Okay. Now it turns out this you can also get that from this equation right here because remember the mass of the object it's just equal to the density of the object times the volume of the object times G. So we have density of the fluid times G times V submerged. And notice the G's cancel. This time the volumes don't cancel because they're different. But what we can do is we can divide V object by both sides and we get V sub over V object times density of the fluid is equal to the density of the object. So then you could get V, moving the densities over, V sub divided by V object is equal to the density of the object over the density of the fluid. Okay, so if you want to, the fraction submerged, this is going to be the ratio of the density of object to fluid. Okay, so get it, you can get the ratio of the volume submerged to the total volume of the object by taking the ratio of the two densities of the fluid, object to fluid, of the object to the fluid. Okay, so this is if you have one of those fraction submerged problems, this is how you could find that. Okay, so if the object sinks, so for negative buoyancy, the idea here is that the force of buoyancy is equal to density. Actually, I'll do this not bolded. Force of buoyancy is equal to the density of the fluid times G times the volume submerged. In this case, V sub is equal just to the volume of the object, so we don't really need to worry about that. But now we know that the force of gravity, or sorry, the force of buoyancy is less than the force of gravity. Now, one of the things that can happen here is that let's just say we have an object sitting in a fluid, and this is negative, so it has F sub g in that direction. I'm actually gonna have it not sitting on the bottom. So we have F sub g in that direction, and we have the force of buoyancy in that direction. And I'll make the force of buoyancy smaller so we can see that. But what's interesting about this is that now this force of gravity is reduced. Okay, force of gravity is the effective force of gravity is reduced. Okay, it's reduced by the buoyant force. Okay, so the F net in the downward direction is equal to the force of gravity minus the force of buoyancy. And again, this time I'm letting down be positive because I know that gravity is going to win because this thing is negatively buoyant, but that's kind of what's going on here. Now, what we have here is we have mg minus density of the fluid, g times the volume of the object. And again, because the submerged volume is the volume of the object. Well, again, you can kind of fiddle around with this and you can say, okay, the density of the object times the volume of the object times G minus density of the fluid times G times volume of the object. Well, what you can see here is you can see that you can factor out G times the volume of the object. So object times G. And then you have the density of the object minus the density of the fluid. So basically, you can get your F net just by comparing the two densities. And the closer that your density, so the higher, let me put it this way, the closer the fluid density is to the density of the object, the closer to weightlessness this thing has. Okay, so when astronauts train for zero gravity, this is how they do it. You may have seen this like in the movie Armageddon. They train underwater, and basically because you can kind of simulate that apparent feeling of weightlessness if you can get these two things to be equal. And this basically applies to neutral buoyancy as well. So for neutral buoyancy, basically it's a similar case, except that the density of the object equals the density of the fluid, which means that this equation, when you have V object times G times the density of the object minus the density of the fluid, this just equals 0, which means that F net equals 0, which means that your force of gravity equals your force of buoyancy. Okay, so that is fundamentally what's going on with that. All right, I do want to do one example just to show you how this works out. So and just to kind of give you some familiarity with how some of these terms are going to be used as well. All right, so what we have here is I'm going to do this problem. Okay. All right, so that's a little too much. All right, so the mass of an ancient Greek coin is determined in air to be 8.630 grams. So mass, just the mass is 8.630. Now, grams, I would change it to kilograms right from the get-go, 0.008630, which means that, so we're doing 4 sig figs. The force of gravity, I'm just going to let G equal 10. The force of gravity is going to be 0.08630 newtons. Okay. And then it says that the apparent mass. So the apparent mass is 7.800 grams. Now, what this means is that what you have is you have the apparent weight. So I'm going to call that F, and that will be, and I'm going to call that apparent weight. Okay. And this one is 0.007800 kilograms. So your parent weight is going to be 0.0863, no, 0.07800 newtons. Okay. Now, basically what this means, what your apparent weight is, this is your F net. So with the buoyant force. All right. So that's what apparent weight means. So basically what it means is it means your apparent weight is going to be your force of gravity minus your force of buoyancy. Okay. All right. And it wants us to figure out we want to know the density of the coin. So the density of the coin equals what? Okay. So what we have here is we have that force of gravity. That's no big deal. But the force of buoyancy is going to be the density of the water times the volume of the coin, because the coin is completely submerged, times G. Okay. So that is how we would do this one. And basically what we're going to do here is we're going to find the volume of the coin using this method. All right. Once we have the volume of the coin, we can calculate the density of the coin. No problem. Okay. So the volume of the density of the coin, we have that apparent force, so 0.07. I'm going to drop the extra zeros. I'm just going to remember to use 4 sig figs. 0.0863 minus density of water is it's 1 gram per centimeter cubed or 1,000 kilograms. And I'm just putting all of this 1,000 kilograms per meter cubed. I'm putting all of this into SI, and we can change to grams per centimeters later. And then the volume is what we're after. And then we have G. Okay, so I'll just say that's 10 right there. All right. Now what we have here is we have we can solve for V sub C, and I'm going to do the algebra really quick. What it ends up being is 0.0863 minus 0.078 divided by 10,000. Okay, give or take. Or it would be, 9,800 if you're using G is equal to 9.8. All right. Now, what does that end up being equal to? I'll just throw that into Desmos really quickly. So 0.0863 minus 0.078 and then divided by 10,000. And what that's going to give you is it's going to give you 8.300 times 10 to the negative 7th meters cubed. Okay, so we will then take the mass of the coin, which we had from up here. So, well, mass of the coin was this right here. So the density of the coin is going to be equal to the mass of the coin divided by the volume of the coin. So that means it would be 0.08630 divided by 8.300 times 10 to the negative 7th. Okay, so I will do that, and I will put this in now, and then 0.00863 divided, need to take this and put it there. Okay. And when we do this, what we end up with the density of the coin is equal to 10,400 kilograms per meter cubed. Now, again, a lot of times you prefer this in grams per centimeter cubed, and that you just divide by 1,000, so that would be 10.4 grams per centimeter cubed. Okay. So that is about what we find correctly there. I'm just going to make sure that um, yeah. Okay. So yeah, that is basically what we'd be seeing there. Okay. So that is just using buoyant force to calculate a volume and then calculate a density. And this is one way you can do this if you're given some of these unknown things. So again, I think the key takeaway is the key formula for buoyant force. Anytime you're dealing with a submerged object, is you need to use this formula. And sometimes, it's not entirely apparent what the V submerged is. It'll be different if it's a sinking object. If it's a sinking object, your V submerged is going to be the volume of the object. If it's a floating object, then not all of the object is going to be submerged. So you got to be careful with that. But in any event, that's about all I have time for. And I think this lecture has gone a little long anyway. So I'm going to go ahead and end things there. Thank you for joining me today. I'll see you next time.